This lesson discusses the concept of universal gravitational force. Many thanks to Michael Bierwald of Bret Harte Middle School in San Jose, California for suggesting this lesson used in his classroom. The law of universal gravitation allows one to calculate the gravitational force between two objects from their masses and the distance between them. The law includes a value called the gravitational constant, designated as g. The value of g is 6.67 times 10 to the minus 11 newtons meters squared per kilograms squared. The value of g is the same everywhere in the universe. Calculating the force between objects like planets, moons, and stars, is possible using this law. This diagram shows an example of how the gravitational force between the Earth and the Moon is calculated. The gravitational force, F, is calculated using the following equation. F equals g times the product of the multiplication of the two masses, m1 and m2, divided by the radius, r squared. In the equation above, F is the gravitational force in newtons, designated by capital N, while capital G is the gravitational constant. This constant is 6.67 times 10 to the minus 11 newtons, meters squared divided by kilograms squared. The two masses are m1 and m2 in kilograms. The function, r, is the center-to-center distance in meters between the center of gravity of the two objects. As an example, let us calculate the gravitational force between the two identical spheres in the diagram above that are touching each other. Each sphere has a radius of 0.3 parts of a meter, and a mass of 1000 kilograms. Substituting the values into the equation shown above gives a value for the force of gravity, F, between the two spheres, of 1.85, times 10 to the minus 4 Newton. On Earth, this corresponds to the weight of a mass equal to only 18.9 milligrams. Obviously, the gravitational force in this example is very weak. Let us now calculate the Earth's gravitational force. The Earth's radius, r, is equal to 6.378 times 10 to the sixth power in meters. The Earth's mass, m, is equal to 5.9742, times 10 to the 24th power in kilograms. The Earth's gravitational force is calculated using the equation shown, where F is equal to the universal gravitational constant, g, times the mass, m, divided by the radius, r squared. The force of gravity that holds us on Earth is then calculated to be 9.79 newtons. However, this value is usually rounded to 9.80 newtons. This is equivalent to 9.80 meters per second squared, or 980 centimeters per second squared. Now let us see what the gravitational force is on our Moon and other planets in our solar system. These bodies exert the same type of gravitational force on objects on their surfaces. The gravitational force on the Moon and each planet is different. The force depends on the Moon or a planet's mass, as well as its density. The denser a celestial body is, the more mass there is under it to hold a person down on its surface. This illustration shows the motion of the planets in our solar system. The motions of Mercury, Venus, Earth, Mars, Jupiter, Uranus, and Neptune are shown. The Earth's moon is not shown in this video. Note that all the planets rotate counterclockwise around the Sun in elliptical orbits. This table lists the gravitational force values in newtons per kilogram for the Moon and all the planets in our solar system. Newtons per kilogram is equal to meters per second squared. Note that the gravitational force on Jupiter is almost 2.5 times greater than that of the Earth. On the other hand, the Moon's force of gravity is only about 16% of that on the Earth. As an exercise in gravitational force, calculate your weight on another planet. How much do you weigh on Earth? Convert your weight in pounds to kilograms. 1 pound is equal to 0.454 kilogram. Select a planet from the list shown in the table on the previous page, then use its gravity value to calculate your weight in newtons. Now convert that value to pounds. 1 pound is equal to 4.45 newtons. If you weigh 100 pounds on Earth, how much would you weigh on Jupiter? Students who wish to solve problems related to gravitational force should visit the website, www.topsofscv.org. Once you have opened the website, click on the tab entitled, Lab Procedures, then view the list of Adobe PDF files shown at the bottom of the page. To access the file named gravitationalforce.pdf, copy the link shown here to your browser. After you are directed to the list of files, move the cursor to the menu on the far right, which shows dotted lines surrounded by a pair of brackets. Click Download to copy the file to your computer. Open the file in Adobe Reader to view the lesson. This presentation was produced as a public service to help middle school and high school science teachers develop experiments, presentations, and demonstrations that can be used in their classes. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website, www.topsofscv.org. TOPS, Teaching Opportunities for Partners in Science, is a program aimed at stimulating greater interest in science by middle and high school students.